Okay, and then the next part we're going to do is look at how a catalyst affects reaction rate. Now, before we even go through the results, you already know that a catalyst only lowers the activation energy of a reaction, and if the activation energy is low for a reaction, it means the reaction will happen faster. It does nothing else to concentration, to temperature, to the amount of particles or collisions. It only has to do with decreasing activation energy, which means that more particles will have enough kinetic energy to take part in the reaction. Right, so let us look on the next page at the results of a catalyst being used in a reaction. Now here we have a reaction, and the catalyst we are dealing with is manganese oxide. So in the first reaction, we are looking at the volume obtained of oxygen without manganese oxide, so without the catalyst, and then with the catalyst with manganese oxide. And here on the first row is the time of the reaction. Right, now if you look at the second row, which is without manganese oxide, so here there is no catalyst, can you see that you have in 80 seconds, you have reached a volume of oxygen of 40 centimeter cubed. Right, so there's 40 centimeter cubed. But if you're looking at the results with manganese oxide, so with a catalyst, you have reached 40 centimeter cubed of oxygen at 50 seconds. So in the first experiment without a catalyst, you reach that same amount in 80 seconds, but with a catalyst, you reach it in 50 seconds. So the reaction rate has increased faster. It's the same thing with reaching equilibrium. Can you see it's staying constant all the way? Which means it reached equilibrium much faster. So the reaction is going to be constant or stay the same much faster with a catalyst. And that's all because of decreasing the activation energy. And if you look at the graph here, with using a catalyst and without using a catalyst, it's not even labeled, but can you see that this graph is steeper, which means the gradient is more, which means the rate of the reaction is faster. So this graph definitely is using a catalyst, and the bottom graph, because it's not so steep, it is without a catalyst. Okay, so all you need to know is catalyst affects the rate of reaction. It increases it by decreasing activation energy. There's no directly or inversely proportional relationship, nothing like that. And another thing is catalysts don't really take part in the reaction, or they don't lose their mass or concentration during the reaction. They just help the reaction happen faster. So if you look at this graph here, it says the mass of an added catalyst, and can you see as time goes for the reaction, the mass stays constant. So the catalyst doesn't get used up in the reaction. It's just there to help it. It's just like a push that the reaction needs. And also here, can you see concentration of catalyst? It also remains the same, because the catalyst just helps the reaction happen faster. It doesn't get affected in any way. It doesn't get less or more. You take it out exactly how you put it in. Right, and the final thing that affects the rate of the reaction is the nature of reactants. Now, you don't need to know too much about this, but let's just look at what happens with the nature of reactions. Now, you have this reactant where you have different metals, and then you're reacting it with hydrochloric acid to form metal chloride plus hydrogen gas. So we have three specific metals here: magnesium, zinc, and iron. Now, when you're looking at all of these three, magnesium is going to attain a faster rate of reaction than zinc, and zinc is going to be faster than iron, only because magnesium is more reactive than zinc, and zinc is more reactive than iron. That's the only reason. So nature of reactants, it just depends on the actual reactant itself, how reactive it is, and that will cause a greater rate of reaction. Right, let's look at example 3. It says here calcium carbonate pieces are allowed to react with hydrochloric acid according to the following equation. Write 3 ways in which the rate of reaction between the reactants can be increased without making use of a catalyst. So they are trying to say we must give 3 ways that what we can do to increase the rate of the reaction, but without a catalyst. A catalyst can be used for any reaction, and it will always increase the rate of the reaction. But let's look at things that are not catalysts. Right, now if you look at this reaction, can you see you have calcium carbonate? And calcium carbonate is a solid. There's it there. S means solid. So if something is a solid, automatically when you think of solid, you should think of surface area. So you can take this calcium carbonate, grind it up into a fine powder to increase surface area, and increase in surface area will increase the reaction rate. The next thing you can do is, if you look at HCl, can you see it's aqueous? And aqueous means it's dissolved in water. It's a solution. And with solutions, concentration can always be affected, it can be changed. So with solutions of HCl, you can increase the concentration of it, and that will increase the rate of the reaction. And another thing you can do is, of course, change temperature. You can heat up the reaction, and this will increase the reaction rate. Right, let's look at example 4. It says 30 centimeters of magnesium ribbon reacts with excess dilute hydrochloric acid at 20 degrees Celsius. Hydrogen gas is produced. The total volume produced is measured every 20 seconds. The results obtained are indicated in the diagram as R, which is the original graph. Right, so the reaction we're looking at here is magnesium plus hydrochloric acid giving you magnesium chloride and hydrogen gas. And this graph is specifically showing us the hydrogen gas, which is this here, versus time. Right, and since hydrogen is the product, again, the graph is increasing because we're dealing with product now. Right, and R is the original chart, so we're looking at R as the one where they used all of these conditions here explained. Okay, 4.1. What causes graph R to level off after 60 seconds? Now, can you see at 60 seconds, R is no more increasing. It was increasing from 0 to 60, and after that, it's just staying constant. Now, we will do later on in other sections something called equilibrium, and whenever the graph is constant, it means either equilibrium is reached, or more simply, the reaction is complete, which means now you're not making any more product, you're not making any more hydrogen gas, the reaction is finished. So that's why there is no gradient, because there is no reaction rate, the reaction is complete. Right, 4.2. What does the term excess mean in the situation which is described above? Now, in grade 11, you did in stoichiometry before excess reagent and limiting reagent. And excess reagent just means you have more of that reactant compared to the one which you have less of. So the one is the limiting reagent, and the excess one is the one you have more of. So at the end of the reaction, you will be left with extra of the excess one. Right, 4.3. Explain briefly how the rate of hydrogen gas produced can be determined from the graph at time is equals to 20 seconds. So they're asking you the rate of the reaction specifically at 20 seconds. And when they tell you one specific time, they're talking about instantaneous rate. Anytime they mention one time in particular, that is instantaneous rate of reaction. And for instantaneous rate of reaction, you are always going to draw a tangent to the graph. So you will draw a tangent to the graph for 20 seconds, and from that tangent you will determine the gradient, and the gradient will give you the rate of the reaction. Right, 4.4. Give 2 reasons why the rate of hydrogen gas production is lower at 40 seconds than at 20 seconds. Now, if you remember from previous sections, every time the reaction begins, so in the beginning of the reaction, the concentration of reactants are always the highest, because you just started the reaction, so you didn't really use up reactants to make products. So because concentration is highest in the beginning of the reaction is always faster. So you will always make more product at that time, and the gradient and the rate will always be higher. And as you are going on with the reaction, the reactants are becoming less, because now the reactants are being turned into products. And as that reactant concentration decreases, you will make less products, because you can only make products from reactants. So if you have less, you will make less. So just remember, in the beginning of the reaction, you're always going to have a faster rate of reaction, which means you will make products faster, and the concentration of products will be higher. And then as the reaction proceeds, it will become less and less until it even reaches equilibrium or completion, which is at all of the points where the graph is now constant and you have no gradient. Right. Which of the graphs graph lines PQST would be obtained if 4.5 only 15 centimeter of magnesium ribbon is added to the same volume of dilute hydrochloric acid. So they're telling you use the same volume, so volume hasn't changed here, but they're telling us that you're using 15 centimeters of magnesium. Now in the beginning, can you see here they said you use 30, so you basically went from 30 to 15, which is half. You have decreased the amount of magnesium, which is the reactant, by half. And if you decreasing the amount of particles by half, it means the reaction rate will also decrease by half, because now you have half of the particles taking part in the reaction. So if the original graph is R and R's rate of reaction is high, it means we need a graph that is almost half the amount of R. And if you look at S, can you see? It's following the same pattern as R, but it's almost half of it because you're using half the amount, so the reaction is half as fast. Okay, next question. 4.6. 30 centimeters of magnesium ribbon is added to the same volume of dilute hydrochloric acid at 25 degrees. So you're using 30 centimeters, which means it's still the same as the beginning. You're using the same volume. The only thing you have changed now is the temperature. You'd increase it from 20 degrees, which they mentioned before, to 25 degrees. So you only increase it by 5 degrees Celsius. Now we know if you increase temperature, reaction rate increases, but since it's only 5 degrees, it's not going to increase that much. So if you're looking for a graph that describes an increase but not that much increase, it will probably be Q, because Q is higher than R, but it's not that much higher because you only increase it by 5 degrees. You didn't double it or triple it or anything that is very substantial. Okay, 4.7. 40 centimeters of magnesium ribbon is powdered and added to the same volume of hydrochloric acid. Now you powdered it. Can you see it's powdered? Which means you have increased surface area, so that means reaction rate is definitely going to increase. And not only did you powder it, you have also used 40 centimeters of magnesium. Before you had 30 and it was not powdered, now you have 40 and it's powdered. So you made two changes. You increased the amount and you increased surface area, which means if you're increasing two things, the reaction rate is going to increase very considerably. And if you're looking at this graph, the only thing that shows a big change or a big increase from the original graph R is P. So P corresponds to an increase in both amount of magnesium and also the surface area of magnesium. Right, 4.8, a major gas leak occurs during the experiment. Now, if gas is leaking, it means you're losing something, isn't it? And in this case, we're only dealing with hydrogen gas, which is the product. So you're losing product. It's going out of the experiment or out of the system it's in because it's a gas. And since you're losing it, it means you're not really having any measurement, and that would be graph T. It's just a constant line because now you cannot measure the rate of the reaction because all of your product is being lost through a gas leak. Right, let's look at the last example. The reaction rate where calcium carbonate reacts with hydrochloric acid, which is in excess, is determined by measuring the mass loss of the components of the reaction in an open flask. The following results were obtained. So you have calcium carbonate reacting with hydrochloric acid, and again it's an acid-base reaction. And since you're dealing with calcium carbonate, you are going to form carbon dioxide and water and a salt. So carbon dioxide, just keep in mind that it's a gas, and gas can leak through a reaction. Right, number 1. Calculate the average rate of gas production during the first 4 minutes. So again here they're asking us for average rate, not instantaneous, average, which means we are going to use 2 points from, which includes 4 minutes, and obviously that is going to be from the beginning to 4 minutes. So all you're going to say is change in mass loss over change in time at 4 minutes. So it's going to be 4 grams, which is at 4 minutes, minus 0 grams divided by 4 minutes, which is corresponding to 4 grams minus 0 minutes, and that will give you 1 gram per minute. And just remember, the units that you actually have in your answer depends on the units they give you. So if they're working with minutes, you will work with minutes. If they're working with moles, you will work with moles. In this case, it was mass, so it's grams, and time was in minutes. Right, 5.2. Explain why a loss of mass occurs in the flask as the reaction proceeds. Now, A mass loss mostly occurs when you have a gas, because gas will leak out of the system. If you're doing this reaction in a beaker, for example, that gas is obviously going to escape. So anytime you have a gas, it's probably a mass loss due to the gas being escaped from the flask, which in this case is carbon dioxide gas. Right, 5.3. Would the rate of gas production increase, decrease, or remain the same if the temperature increased? Now, obviously, you know, temperature increases reaction rate, so it will definitely result in an increase in reaction rate. Right, next one. Give a reason why the loss in mass remains constant after 6 minutes. Now, if you look at 6 minutes, can you see the mass loss is 5.2 grams? And as you go into 7, 8, 9, 10 minutes, you are now remaining constant at 5.3 grams, which means anytime something remains constant, this is when the reaction is complete or it has reached equilibrium. And the reason why it's complete is probably because you have used all of the reactant, because once the reactant is finished, you cannot make any more product. If you don't have ingredients, you cannot make something. So if you don't have any reactants, you can't make products. So you probably used up all of the calcium carbonate or whatever other reactant that was involved in this reaction.